Okay. Thanks a lot, Veronica. Okay, so let's begin by recapping the last lecture. We started by outlining a prescription for computing the entropy in black hole background. We did this by a sort of a series of tricks, or a series of CFT tricks, and then we applied this to compute the entropy of the bath in this two-sided eternal black hole, and where this bath you can think of as the Hawking radiation. The result at face value led to this bags of gold issue, where it seemed that the black hole, at least, the black hole at fixed energy, was able to support an arbitrary amount of entanglement entropy with the bath. And then we also discussed a hypothetical situation, which I described as the information loss scenario, where due to some, I assumed, some gravitational effects. Was there a question? All right, never mind. Yeah, so I described this information loss scenario where due to some gravitational effects that maybe the wormhole entropy can be fixed somehow, but we sort of stay with the semi-classical answer for the Hawking radiation, and then I showed how that led to information paradox, and finally I talked about the unitarity scenario and how that opened up many other questions, one of which is the possibility of a firewall. So that's a brief recap. Any questions on anything from last lecture or anything? Okay, there are none. Let me move on. So the question in this lecture, well, the question I'm going to start with, it's kind of the question of where we ended last time, which was what's our mistake? Where does the semi-classical picture or answer go wrong? The claim is that essentially we've been using a wrong formula. The formula we've been using does not underline the not, does not take into account the fact that we have a gravity theory. It does not take into account the gravitational nature of the theory. And I will discuss today a new formula which comes from taking into account non-perturbative quantum gravity effects, but I will sort of prove this. I will derive it next time in my final lecture. And some of the motivation for this formula comes from holographic entropy in ADS-CFT. Although it seems to, I don't know if the right word is supersede holography. This formula that I will talk about today comes purely from gravity. And in some sense, you can think of it as the origin of where holography comes from. Okay. I will introduce the formula. Oh, I should emphasize that you should have seen a version of this formula, I think, during Netta's talk on quantum information and ADS-CFT. I'm going to I'm going to go over the full formula from the beginning to the end. I'm not going to assume much. Okay, so this formula now goes by the title of gravitational fine-grained entropy, I will introduce the formula, and I will at the same time apply it to an example. So let's suppose we want to compute the entropy of some region Q, which is supported on the bath region, plus possibly part of the ADS boundary. So let's actually consider a concrete example. So let's consider this interval here. Sorry, a sec. Okay, so let's call this region Q. Okay, and the way to apply this new formula is to consider, the first step is to consider codimension 2 surfaces in the bulk. Codimension 2 in our case is just a point. Okay, and so this point is X. Let's just call it here, X in the ADS region that are homologous to the intersection of the boundary of Q and the boundary of ADS. Okay, so what this really means is that when Q intersects the ADS boundary, the surface X has to be homologous to this point here. So let me mark that in red. Sorry, one sec. And what does homologous mean? It means that there exists a space-like codimension 1 ADS region, which I will call sigma X, that is bounded by the union of X and this intersection of Q and the boundary of ADS. Okay, so it's this region here. This is sigma X. Okay, I should also say it's space-like and also achronal, but we can discuss that if somebody has a question later. Why I'm specifying that. You'll see an example where this refinement here is important. Anyways, so having specified X and sigma X, one then considers this functional here, which is the generalized entropy of X. So this is a generalized entropy. Which is composed of an area term phi naught plus phi x over 4g Newton. I'm calling the dilaton an area term because of what we discussed last time, plus the entropy of the matter CFT on the region, on the union of sigma x and q. So on this entire interval here, from x all the way to the boundary, to this boundary of Q. And what this hat symbol here means is that we're considering the entropy in the semi-classical state. So in the first lecture, I discussed at length how to define the semi-classical state in this spacetime. And even though the semi-classical state led to problems that I discussed in the second lecture, but here you're supposed to assume it regardless. Okay. Let me see what else. Oh, something I forgot to mention. I wanted to give more examples of homologous surfaces. So this here is an example of a surface X that is homologous to the boundary of ADS. But here's another, the union of these three surfaces, X1, X2, and X3 are also homologous to the boundary of ADS because you can consider a sigma X like that. So a sigma X could be, for example, a union of these two intervals. The boundary of these two intervals is, it satisfies this condition here. Okay, just wanted to emphasize that. I'm not going to consider things like this for the moment. I will come back to it later. Was there a question?
Yeah.
Go ahead.
So I noticed that here you're considering only the homology constraint. It's only on the intersection of the boundary of Q with the boundary of ADS. And there, like, I understand that from like, the W orography point of view, but is there a way to understand why it's not homologous? That you take the homology constraint only on that side of the interval Q,
Yes, there is.
and not on the.
Yes, there is. It follows from how this formula is derived using the replica trick and things like that, which I will discuss tomorrow.
Thank you very much.
Yeah, you're welcome.
And we're assuming a non-degenerate case in higher dimensions, for example, we would have non-degenerate case. Well,
Sorry, degenerate case. Degenerate, you mean multiple? So what do you mean by degenerate?
Well, sorry, are we uplifting it to higher dimensions at all?
No.
Or? Okay.
I'm not. But can you tell me what happens? What can go wrong in higher dimensions?
Well, you could have the boundary of Q can be lower dimensional when it's intersected with the boundary of ADS. More than just codimension, higher codimension than 1. So you would have to, one would have to.
Sorry, how so? I mean, Q is a codimension 1 surface or region. Its intersection with the boundary has to be codimension.
It could be like a
2.
on a coming on a wall by touching at a single point or something. But never.
Okay, I can't. I've been working with 2 dimensions for so long now that I can't imagine higher dimensional surfaces and so on. So maybe we can take this offline later. I'm actually interested to understand these weird situations.
Okay.
All right, thanks.
Sorry for the interruption.
No, this is fine. This is good. Okay, so okay, so far I just defined the class of surfaces one should consider. Okay. Next, we have to focus on the surfaces X that extremize the generalized entropy. So we should consider, so focus on surfaces X that extremize this entropy, meaning that surface X where the first order variation of the generalized entropy of X, which can be written as like the derivative with respect to the location of the surface, so y mu say, is equal to 0. So this is the location of X. Okay. And surfaces that satisfy this condition are called, well, I would label them as X ext for extremal, and they're often called quantum extremal surfaces. Okay. Here, quantum extremal surfaces, it's as opposed to classical extremal surfaces. Which are those that extremize just the area part of the generalized entropy. So in our case, that's d phi of x dx. Or actually, let me try to study differently. So variation of phi of x over 4g Newton is equal to 0. The surface is still classical. It's just the reason why it's called quantum is because you're extremizing the entropy with the inclusion of the first quantum correction. That's this matter von moment entropy term. Also, these surfaces, sometimes I'll just call them QES, just abbreviate quantum extremal surface. Okay. It could happen that there are multiple, you find multiple surfaces X that extremize the generalized entropy. And in that situation, you impose a so-called minimality constraint. Oops. Minimality constraint on the entire thing, and you pick the one with the smallest generalized entropy. Okay, so here you minimize over all quantum extremal surfaces. Okay. I'm going to apply this now to this example in a bit more detail. But before I do that, are there any questions on this slide?
Yeah, question.
Go ahead.
Is this a definition or a claim? This equation, is it defining S or is it a claim between the equality of two sides?
For now, I am defining S. In tomorrow's lecture, I will derive that this is the correct formula for computing the von Neumann entropy of a Bath region Q.
Okay.
Of any Bath region Q. Yeah.
Sorry, oh, go ahead.
Oh, thank you. I have a question, and the question is, so you said you can derive this formula independent of like holography, it just comes directly from gravity. So then how do you define it for an asymptotically flat background?
I don't think anyone knows exactly how to define it for asymptotically flat cases where gravity goes all the way to infinity. But there are proposals, but we're getting ahead of ourselves.
Thank you.
Mm-hmm.
Yeah, sorry, I just had a question about, I guess, in this formula where you have the semi-classical von Neumann entropy. So that does that region Q union sigma X, does that include like some region on the ADS boundary?
I mean, it does, yes. I mean, here the ADS boundary is included in this region.
Right. I guess. Yeah.
on.
So what is the? I guess I don't understand what exactly is the semi-classical state on that. Yeah, I guess exactly on the boundary.
Okay. So let me first say, so the way that we defined the quantum state last time, or the time before that actually, was that to Weyl transform away the ADS space. And so then you had flat space everywhere. And we had some quantum state there. And then we Weyl transformed back in the ADS space. So do you remember that discussion?
Mm-hmm, mm-hmm.
So that for us defines what the quantum state is everywhere. There are actually some subtle issues right at sort of this point. Basically because the Weyl transformation is discontinuous at this point.
Mm-hmm.
And that actually causes the stress tensors to be infinite at the ADS boundary. But you get a delta function that remains at the boundary and it doesn't go anywhere. So we interpret this just as a funny feature of this model. You can imagine a more realistic situation. Like if there was, in a more realistic situation, there would be a smooth transition from the flat space to the ADS space, and which would tame this divergence. But so far it looks like we know it's there, but it doesn't seem to pollute any of the important calculations.
Okay, great, thanks.
Yeah, welcome.
Just a quick follow-up question on that.
Mm-hmm.
So before you said that we're not treating the boundary particle as dynamical. So if you actually treated it as dynamical, would that be the same as sort of smoothly interpolating between the flat and the ADS space?
So let me first correct something. We are treating the boundary particle as dynamical. However, we're considering a static state. So we have a solution where the boundary particle does nothing.
Oh, okay.
It doesn't do anything interesting.
Okay, thank you.
Maybe you're touching on another important point, which is, so the boundary particle, it's a degree of freedom in the system, but it doesn't appear anywhere in this formula. In principle, there should be a plus S of the boundary particle. There is some entropy that you would get from the boundary particle. It's going to be a quantum contribution, but we're assuming, well, we're assuming the following thing. We're assuming that 1 over g Newton is much larger than c, where c is the central charge of the matter theory. This S here is proportional to c, which is much larger than 1. So we have a large number of species of the CFT, and the boundary particle gives you an answer which is order 1. It's just one particle. So the entropy contribution coming from the fluctuations of that particle would give you a contribution here which is of order 1, and so we don't expect that it's going to have any significant effect. I don't know how difficult it is to get the contribution from the boundary particle. Maybe somebody worked it out somewhere, but because we're working in this regime, we claim that we can ignore it. Any other questions?
I have a follow-up question to the question was asked before about the generalization to flat space and the fact that this formula of entropy is general. So maybe you'll talk about this tomorrow, but the assumptions that are behind that are the assumptions only that the Euclidean gravity path integral is well defined and works well, and is that the reason why in flat space-time this is a problem, because you don't have, like, we're not that sure that that works well?
No, we're not sure. We're not sure Euclidean gravity works anywhere. The analysis that we're going to do tomorrow is just to focus on the Euclidean path, the Euclidean gravity path integral, or rather to focus only on saddle points of the Euclidean gravity path integral. The troublesome part here is that, again, this is a question really for tomorrow, but here we are able to specify the location, the interval that we want to compute the entropy of in a gauge invariant way. We say it's in the bath, it starts at point from the origin to some point 1 or whatever, x or whatever. We can specify it, and this is a gauge invariant thing to do. But if you have gravity everywhere, and you're trying to do a path integral where you're summing over all different geometries, then it's not clear how you specify the location of where Q is. On any given geometry, you can specify a location, but you can't, like if you fix a gauge and so on, if you know what the solution is, but you can't specify it. You can't identify the same location in different geometries. Is another way of saying it. Or said differently, the location of Q cannot be non-perturbatively well defined if gravity is everywhere.
So the reason is basically that the gravitational path integral is not clear how to make a gauge invariant, that you cannot, that you're able to specify the location of a point in the gravitational path integral by fixing a gauge, but you cannot actually, like you cannot basically define the gauge invariant measure for the path integral.
I would just say that you cannot specify the location in a space. Well, you cannot specify an interval in space-time in a gauge invariant way in the full path integral. That's what I want to say. Okay, so let's move on. So let's consider the example of a single interval, again, which, single interval that we drew on the previous slide, and let's restrict that interval to lie completely within the t equal 0 slice. You can argue, due to symmetry of the problem, that you should expect the extremum of the generalized entropy to also lie on the t equals 0 slice. The relevant quantities that we need for this extremization are the dilaton and the matter, the dilaton and the matter entropy on the slice. So the dilaton is just given by this thing. Over here, I have the plot of these quantities. The dilaton starts very large near the boundary, and it just decays to some value at the horizon. And the matter entropy does something similar, except that it decreases first, starting from the horizon. It decreases first, and then it grows. And it's given by this expression here. So two things need to be true in order to successfully find an extremum. The first is that the two terms need to have opposite signs so that they can cancel. We want this thing to be equal to 0. Which you can check is indeed the case if you look at this highlighted region here. The dilaton has positive slope as you go away from the horizon, while S has a negative slope, so that's good. The other thing is that we need that the derivative of phi, dA phi, to be sufficiently small. In fact, we need it to be to go as G Newton over C. Basically, in order to offset the 1 over G Newton that sits out front of d phi, and in order for it to be comparable to the second term, and so that they can actually cancel. So in some sense, we need we can find, well, a quantum extremal surface will lie near a classical extremal surface in some sense, although that doesn't have to be strictly true. But the point is that phi has to be shallow, like this, as drawn over here. So here, remember that the bifurcation surface is actually it is a classical extremal surface, and so the derivative of phi is 0. So if you get sufficiently close, you can make d phi as small as you want. Okay, and then ultimately, so you'll find the quantum extremal surface, and it's near, but it's outside the event horizon. It's like a location there. So let's say, and so if you actually solve this equation and you work in the limit when b here is the size of the region Q in the back. If that b is small, then you get an expression which looks like this: A is equal to b plus beta log of this quantity. And if it turns out that this quantity here can be thought of equivalently as the difference between the Bekenstein-Hawking entropy of the black hole minus the ground state entropy. So S naught here is just phi naught divided by 4G Newton. So it looks like you have something which looks like a scrambling time here, okay? And another thing about this example is that there are no other quantum extremal surfaces. This is the only one that you have. So we have a quantum extremal surface outside the horizon, but it's very close to the event horizon. And so the generalized entropy, when you evaluate it on this quantum extremal surface, you find that it's well approximated by the Bekenstein-Hawking entropy of the black hole. Plus dot, dot, dot. Let me note something. So here, I'm basically saying that that the area that the entropy of Q is well approximated by the area term. That's basically what I'm saying when I say let's just focus on this. But this does not conflict with the fact that to find the quantum extremal surface, those two terms are comparable. Right? So the point is that it's okay for phi to be much larger than S, or phi over g Newton to be much larger than S, while also having that the derivative of phi over g Newton to be comparable to the derivative of S. I just wanted to emphasize that point. Any questions on that?
Sorry, I probably just missed this, but in the plot, the value of the dilaton is non-zero in the bath, or?
No, it's so this plot, the bath is here.
Oh, okay, thank you.
So this is meant to be the ADS boundary.
Oh, sorry. So what's the yellow region then? The highlighted part.
That was supposed to be the region where the derivatives of phi and S have opposite signs.
Okay, thank you.
Yeah.
Question?
Any other? Yes, go on.
Yeah. The matter entropy part usually comes with a cutoff. How did you fix that cutoff? There's an epsilon. There should be.
Yes, there is indeed an epsilon. There's a cutoff.
Yeah.
Well, that cutoff is irrelevant in finding the extremum, because the cutoff does not depend on will not depend on A.
I see.
Yeah. And then here, yes,
but
there is
in general, the entropy depends on the cutoff.
Indeed. So here there's a plus log epsilon. Okay. And indeed it's there. The usual statement that people make is that here we have phi over g Newton plus log epsilon, something like that. And by this epsilon, I mean it's the epsilon of the cutoff near this point. Okay, there's also a cutoff here, but let's ignore that. Let's focus on the cutoff here. The statement is that this cutoff is can actually be reabsorbed into this g Newton. So in terms of you should think of this g Newton as the bare g Newton, how you study in normal quantum field theory. You start with bare coupling, so this is bare, and then this log epsilon renormalizes this bare cutoff, this bare Newton's constant, and so then you get phi over g Newton renormalized. Okay. Actually, I cheated. So what I discussed is what happens in sort of more generally, but in this actual system, like JT gravity and this matter, you should think of it not as renormalizing g Newton. Well, this might be really the same thing, but you should think of it as renormalizing phi naught. So we had a phi naught over g Newton plus log epsilon. You should think of this, so it's a phi naught that is bare, and then this becomes phi naught renormalized over g Newton. Usually people absorb g Newton into phi naught, so sometimes this distinction doesn't really doesn't make a difference. I hope that answered the question.
Yeah, but the other end, like where there is no gravity, how does that work out? Like,
it's there. It's there, and we can't do anything about it. We're just imagining that it's there, and it's some large number that is fixed as a function of time. So it's not going to factor into anything really. And you'll see in all of our examples, we're always going to be comparing several sort of different, we're going to be comparing the generalized entropy evaluated on different bulk surfaces, all of which have the same endpoint in the bath. So they all share the same cutoff in the bath. So it doesn't really factor into comparing different answers and so on. Like it's always the same. It's the same log epsilon that just goes through the entire calculation. It doesn't really have any. It doesn't seem to have any important consequence.
Okay, thank you.
Yeah, welcome. Okay, the thing I wanted to say next was the relation of this result to regular holography. For holography, one imagines that the two ADS boundaries, this guy and this guy, can be replaced with two quantum systems, left and right. Right now I'm talking about regular holography with no external system. And using the quantum generalization of the RT formula, or essentially the formula that I described in the previous slide, the Engelhardt-Wall formula, or I don't know if there's another name for it. One finds that the quantum extremal surface, if you're computing the entropy of the right, is simply the bifurcation surface. Okay, so this captures this bulk calculation in holography is meant to capture the entanglement between the right boundary and the left boundary, the right quantum system and the left quantum system. In our case, you can imagine a similar thing. You can imagine that that our model is actually, we start with the same right and left systems as we had in this case, and then we couple them to these external baths, BL and BR. And when we're computing the entropy of the region here, the Q of the previous slide, it's like we're computing the entropy of R here. And so then this surface right here is meant to be, it captures the von Neumann entropy of this dual quantum mechanical system. Okay, and I want to claim that the way you should think about this is that it's computing the in both calculations. You can think of this as computing the entropy of the right black hole as seen from the outside. There are some differences in these two cases. The first difference, well, is that here the quantum extremal surface is at the bifurcated horizon, but the quantum extremal surface here is not quite at the bifurcated horizon, and this has important physical consequences, which I'm going to discuss more later. We saw from the previous slide that the scrambling time made an appearance, and that's actually this time difference here. So this is T scrambling, which goes as beta log S Bekenstein-Hawking minus S naught. Okay. I will discuss the physical importance later. Something else I wanted to say was another difference between these two cases is what happens under time evolution. So let's suppose you consider the system R at a later time. Well, the quantum extremal surface doesn't change. It's the same. It's the same thing. It continues to be the bifurcation surface. And the quick argument for this is that this system has a boost symmetry. So I can, under moving time up, I have a symmetry like that in the bulk. But this symmetry, but the bifurcation surface is a fixed point of that symmetry. However, in this case here, if I apply the same symmetry, I would evolve this point upwards. It would come, oops, it would go up here, but then by the same symmetry, this point here would evolve to a point there. Okay, so as a function of time, in this case, the location of the quantum extremal surface moves, and we can, it just follows from boost symmetry. And it also follows just physically. Like you should expect things to change because R, as a function of time, it's interacting with the bath. So there's information coming in and information going out and so on. And the manifestation of that interaction is this motion of the quantum extremal surface. Any question about this? I will say more about this later.
What did you mean by the right black hole?
Good. I really just meant it's the entropy of the black hole as seen from the right exterior. So like if you're an observer here, let's say you're near the boundary and you're floating around, and you're asked what is the entropy of the black hole as viewed from the right, you would say it's this entropy computes that.
Okay, but isn't the situation symmetric? Like if I'm observer on the left side, shouldn't I see the same entropy?
Yes, exactly. So in this situation, you get the same answer for the left and right black holes. Good. Well, yeah, no, you're right. I kind of see what the confusion is. When I wrote this down, I was just giving an interpretation to this specific calculation. But if you consider this calculation, that would capture the entropy of the black hole as seen from the left. And because of the symmetry that you just quoted, you should get the same answer.
Okay, yeah, and that's true for your when you couple it to the bath as well, right?
Precisely.
Okay.
Any other questions?
What would the scrambling time look like on this, I guess the picture on the right where you drew this like time evolved arrow?
Good. So I would again draw the dotted, just a null. It's so this scrambling time. It's a scrambling time to the past and in falling coordinates. So it's going to be the difference between this thing here and this thing there. That will be the scrambling time.
Thank you.
Yeah.
Just a quick question. So the dotted line that you're drawing, is that does that have something to do with the representative trick?
This dotted line is just meant to be a null line drawn backwards from that point.
Okay.
So far, I'm just making a geometric statement that if you start from the location of the quantum extremal surface and you evolve backwards along a null line towards the boundary, you would hit the boundary. Well, you'd hit the boundary at some point. The time difference between this point and this location here would be a scrambling time. So far, I'm just making a geometric statement, but I will talk about its physical implications more towards the end of the talk.
Okay. Okay. Thank you.
Okay. Okay. So now let's. Okay. So the calculation so far was about what happens when you. Well, we considered an interval on the boundary that contained one of the ADS boundaries, and we said that this computes the entropy of the black hole. So in order to compute the entropy of the wormhole, naturally you should consider a boundary interval that contains both ADS boundaries, and that's what we will consider. So let's consider two intervals. Let's discuss the two interval case that includes both ADS boundaries. Okay, so that's like Q here. Guess I should have. Oh yeah. So Q, we're computing now the entropy of Q, which is composed of QL and QR. Okay, and both of these systems they contain the two ADS boundaries. So again, the first step is to identify the homology surfaces or points, if you will. And there are two classes. The first is an extension of the last example, which we can call the disconnected surface. And so that's going to be basically 2 points here, one XL and XR. And they have corresponding homology surfaces or homology regions that connect XL to this ADS boundary and XR to this ADS boundary. Those are the two regions, sigma L and sigma R. The generalized entropy evaluated on this homology class looks well, it looks something like this. The notable thing about this is that now it involves a two interval entanglement entropy. It's a two interval CFT entanglement entropy. Right there, we have two intervals. This guy here and this guy there. And the requirement to, well, having so far we defined the homology class. Now we need to extremize. So we require that delta XL of Sgen is equal to delta XR of Sgen is equal to 0. So we have to extremize over both points. Okay, these are two separate extremizations. We have to do it like this. So that's one class. The other class is called the trivial surface, where there simply is no x in the bulk, and so the homology region is it has to extend from this ADS boundary all the way to that ADS boundary. So the homology region is this sigma phi, and because there is no x is the empty set, the generalized entropy is just the matter entropy evaluated on this interval. And so because there's no x, the extremization is automatic. So the variation with respect to nothing is clearly equal to 0. So this thing is automatic. Okay, so these are the two options. I mean, there could be other options, which I won't discuss, but there could be other options. For example, you can consider, an island here. Well, sorry, I didn't introduce that term yet. But you can have another some disconnected surface here. It's not connected to anything. This would also be homologous, but that's not going to be relevant for this calculation. Turns out that you can't find an extremal disconnected surface in this situation. By disconnected, I mean disconnected from everything. Any question about these two options? Okay, I'm going to analyze these two contributions in detail, and also what they, how they evolve under time evolution, and we'll see what they tell us about the entropy of the wormhole. So let's start with a simpler case, which is the trivial surface. Thankfully, we don't have to do anything because we already did this. So this is just the von Neumann entropy of this interval here, and it's just the entropy. Well, it's just a matter entropy, so it's just a semi-classical or entropy of this interval in the semi-classical state that we studied before. And under time evolution, well, it just evolves upwards. So it's going to look something like this. Under time evolution U. And the answer is what we got last time. This was this log of Koch, which for sufficiently late time became transitioned to being linear in time. So this is time here. And so this assigns the wormhole an ever increasing entropy as such. This looks a bit worrisome, but it's fine because we're not done. Okay, any question about the trivial surface? Okay, so let's talk about a more interesting case. This is a bit involved, so I'll go slow. So this is now the disconnected surface. So the generalized entropy looks something like this. it's a sum of area terms, one for each point. And you have this von Neumann entropy of the disconnected of these two intervals. This thing is hard to compute in general. The reason is that it's, I hope you guys are familiar with this from Cassini's talk, that the von Neumann entropy of two intervals, in order to compute it, you need to evaluate a 4-point function of twist fields. So this is a 4-point function of twist fields. And the issue is that it depends on, because it's a 4-point function, it depends on details of the CFD. But we are interested in sort of general results that don't care about those details. And it turns out that there is a strategy for extracting those general results. The strategy is the following. So the first step is to simply assume that this 4-point function factorizes. Okay, just assume that. And then because, well, if it factorizes, then the von Neumann entropy of the union of the intervals becomes simply a sum of the two von Neumann entropies. Okay, so that's nice. And okay, so let's assume that. So now the entropy breaks up. Then what we can do is we can just look for quantum extremal surfaces. So we have these, okay, so it factorized, now we can look for quantum extremal surfaces. The idea is that this is going to be easy. The reason is that it factorizes into two separate single interval problems, which we discussed in the previous slides. Okay, so it's one problem on this side and a separate problem on this side, because everything factorized. And so you need to do this and find the locations y2 and y3, which extremize the entropy. These two points y2 and y3 will depend on u, on time. So here I'm imagining that we are doing this when we can do it at t equals 0, or we can do it at some later time u. It'll depend on that time. And the final step is to trust this answer only in the regime where the 4-point function actually factorizes from sort of general CFD principles. What I mean by that is you trust it only in the regime where you have a certain OPE limit, basically where y1 is close, sort of goes to y2, and y3 goes to y4 in this limit. Or maybe said differently, it's a limit where the cross ratio, I think, I don't know how it's usually defined, but it's where the cross ratio, say, goes to 0 or goes to 1 or something. Basically, the statement is that y2 is much closer to y1 than it is to any of the other operators. So the 4-point function factorizes into the two 2-point functions. Okay, and it turns out that you can find these extrema. So you can find these extrema, and they satisfy sort of this condition here that you have this OPE, you're in some OPE limit after some time here. there's some delta t here. The details of what delta t is not important. But after some time, indeed, these two, this answer that you get from this strategy is justified. Now, let me say that in this answer, the result that you get is that y2 and y3 are near the horizon, and because remember that this is just like this single interval problem, which had this property, and since it's two single interval problems, the value of the generalized entropy is twice the Bekenstein-Hawking entropy. I guess I should have emphasized before that because of this boost symmetry that you have, it's a constant in time, it doesn't change. And so that's why I drew it as a flat line there. Okay, this was a lot, so please ask me a lot of questions.
Sorry, go ahead.
Thanks. So you mentioned that your y2 and y3 are close to horizon. So doesn't that violate the OPE limit?
No, it does not. So actually, good question first. It depends on the time u. At t equals 0, so if you're here, then indeed y2 and y3 appear to be much closer together than they are to y1 and y4. So the OPE limit is not trustworthy when u is close to 0. However, as you time evolve upwards, up to this time, so as you evolve this slice to a slice up here, this point evolves this way, and this point evolves that way. So y2 and y3 are actually they are getting farther away from one another, and they're getting farther away from one another, and so y2 becomes much closer to y1 than it is to the other two, and similarly for y3 and y4. So this is what I meant by the statement that as you time evolve, that for some period of time, the OPE limit is not justified, but eventually it will be justified. Does that make sense?
Yeah, that makes sense. Thanks.
Mm-hmm.
I have another question on this point.
Yes.
So this growth of interior makes those 2 points far enough, let's say, and so you have, I guess, approximate factorization, right? It's not an exact factorization.
Sorry, can you I missed the first 2 words of your question.
Oh, sorry. I was saying that when you evolve and the interior grows, you have this factorization, but I guess this factorization is approximate. It's not exact, right? So yes. I don't know whether, like, how big are these errors, and if that can create a problem in actually finding the actual location of the quantum extreme surface. Yeah, that's a really good question. But unfortunately, it depends on the details of the CFD, how fast it quote unquote factorizes. It never factorizes exactly, but the question is, what are the errors, or what are the corrections to the factorization, and that depends on the details of the CFD. But I should say that you don't actually. So factorization is not necessary here. It was a trick in our case to actually be able to compute something in general. If you have the 4-point function for all times, you can just look for the quantum extremal surface at all times. You can find the quantum, I would bet that you would always find the quantum extreme. Well, actually, no, is that true? Hold on. No, I think, okay, the statement that I was going to make was that
you would always find a quantum extremal surface at any time. But I think there are examples where there is simply not a quantum extremal surface near t equals 0. So there are examples where we know what the 4-point function is exactly, and it's just like you try to solve this. Let me write it down. You actually try to solve ds equal to 0, and you just don't find a solution, even though you have the full 4-point function. And you need to time evolve a little bit, then you find a solution. So yeah, anyway, so these are a series of comments. The most important takeaway from what I just said is that the 4-point function does not have to factorize in order to find a quantum extremal surface. We wanted to make a general statement. That's why we appealed to factorization.
Okay, so there is no guarantee that unless you know the CFT you're talking about, there is no guarantee that you can just assume factorization, find your quantum extremal surface, and that is actually the quantum extremal surface, the real one, which would be the one where you don't assume factorization. You don't know how close the two are if you don't know the details of the CFT. Is that right?
Yes, I would offer just one minor correction. I think a CFT 4-point function will always factorize approximately at sufficiently late time. The question is going to be at what late time, at what time can you actually start to trust this this factorization as sort of as a good approximation to the location of the quantum extremal surface.
Okay, thank you. And when you don't have the quantum extremal surface, then it just denotes the trivial surface to dominate, I guess? Or is there any?
Yeah, I'll discuss that now on the next slide. But you're right. Yeah, so in this region here, let's say, let's suppose that there is no disconnected surface, then it's only the trivial surface that's in the game, and so the entropy has to be given by that one.
Great, thank you.
Mm-hmm. Okay, so any other questions?
I have a question.
Please.
So when you time evolve in U, could you maybe just illustrate what the foliation looks like?
Good. So the important point here, well, okay, let me see, how should I draw this? So I'm imagining that both this point and this point are on the t equals 0 slice, okay? And then I'm evolving them both by equal amount of bath time. By that I mean I evolve them both by the same generator, the boost generator. So it's a slice that's gonna, it's these slices that look like this, and so on and so forth. So these are the slices that do this. They continue in the bulk in this way. Does that make sense?
Yeah, thanks.
Mm-hmm. I guess maybe I should also say that the bath metric, dy plus dy minus, is du squared plus d sigma squared. I'm just evolving by this u. That's what I drew there. Okay, if there are no further questions, I'll move on. Okay, so we have two options. We just went over both of them. And the last thing to do is to apply minimality. Right? So we found extremal surfaces. Now we apply minimality. And the actual entropy of Q is going to be given by the minimum of these two homology classes, or these two surfaces, which in our case, one is given by twice the Bekenstein-Hawking entropy, and the other one is given by this linearly growing piece for all time. And so we get the page curve, because when you apply minimality, the evolution looks like this. The entropy of the wormhole is is, oh yeah, I should emphasize that this is for the wormhole. Okay. And so we managed to avoid the bag of gold issue. So no bags of gold. Awesome. Any question about the application of the minimality condition?
Is there any danger that the assumption of factorization kicks in after the page time, where you only have the trivial saddle?
If one does find something like that, then we're back in we're back in square one, right?
Sure.
Because then we'd have information paradox again.
Mm-hmm. So I guess maybe a follow-up, the cases where the 4-point function is known exactly, this just doesn't happen.
Correct.
Okay.
It doesn't take too long, actually. Let's talk about timescales. This timescale here is something like, I don't know, beta times S von Neumann. Oh, sorry, S Bekenstein-Hawking, roughly speaking. Right, because I'm just equating, I'm equating this, I'm equating this to this. So that's going to be time is going to be roughly, so yeah, so U is going to be roughly, yeah, just beta over C as Bekenstein-Hawking. That's a very long time. It turns out that the cross ratio that I talked about before, well, the cross ratio who's that controls the factorization, we call that X. It goes as e to the minus beta times U. Okay? So when this thing is small, this thing controls the how far you are from factorization, roughly speaking. And if this is small, then it means you factorized. Clearly, I just need like U to be roughly like, I don't know, 10 over beta. And this is a pretty good, this is going to be really, really small. Now imagine what would happen if I put U is proportional to S Bekenstein-Hawking. Oh, did I get the betas wrong? Sorry. Beta times 10. So if I put something like this, okay, it's really, really small. So you can sort of bet that no CFT would be far away from factorization by this time.
Makes sense. Thank you.
Yeah. Okay.
One question. If you're going to
Yes.
answer this in 5 minutes, do let me know. Here you're happy that you recovered the page curve, but isn't this the information loss scenario?
That's
Are we
exactly what
losing
I'm
information here?
Okay, that's my next slide.
Okay, sorry.
What about the radiation? Okay. So far, we have the wormhole had a page curve, but the radiation doesn't, right? So this is information loss. The radiation is not gravitational. So why should we expect anything new to happen there? So it's true that the radiation is not gravitational. However, it is interacting with the theory of gravity. Like, if you will, the state that was prepared on the radiation and the gravity region was a path integral that depended on gravity. So maybe some of this gravitational aspect leaks into the radiation and fixes things there. For today's talk, I'm just going to apply the gravitational fine-grained entropy formula to the radiation. And see what it gives, and then justify it tomorrow. Okay.
By the way, you have about 5 minutes.
Oh, snap, really?
I think this time I did get it right, but yes.
Oh man. Okay.
Well, you can keep.
Okay. Let's see how I do. Okay. So thankfully, we already did all the work. So let's talk about computing the entropy of the radiation. Yeah, in my mind, I was thinking, oh yeah, I have until 7:15. Okay, no, never mind. Okay, so let's compute the entropy of the radiation. By that, I mean this union of the complement of the Q's of the previous section, but within the bath region. Oops, sorry. Let me see. My notes. Okay, so again, there are going to be two possibilities. Something which I'll call the island contribution, which is given by a class of surfaces in the bulk. Notice that this is homologous. This region here is homologous to the union of, well, I had this weird thing where I said it was an intersection of Q and the ADS boundary. Now there is no ADS boundary, so this what I'm trying to say is that this region here is homologous to it is homologous to nothing, I guess is what I'm saying, right? Maybe I shouldn't belabor this point. Okay, maybe if somebody asks me a question, I'll say more about it. But the point is that one such surface you should consider, if you apply the formula to this region Q, looks like it's like the union of XL and XR. The generalized entropy will look something like this. That's okay. And then you need to extremize with respect to XL and XR. Okay, so that's one contribution to the entropy. Another contribution I'm going to call semi-classical or the trivial surface, where there is no bulk region. And again, well, the entropy in this case is just going to be the entropy of the bath regions, QL and QR. And so it's just given by the matter entropy in the bath, okay? And the extremization is automatically enforced, or it's just automatic. And the claim is that this is isomorphic to the previous calculation. And it relies on the fact that, which I'm going to say on the next slide, it relies on the fact that we have that the matter state on the global spacetime is pure. What this means is that the entropy of, say, QL union sigma L, sigma R, and QR, which is what we had before. So this region and this region is going to be equal to the entropy of this region, and this region, because they are complements. Okay, the total matter state is pure. So these two are equal. And similarly, if you compare the trivial surface with a disconnected surface, sorry, the trivial surface with the semi-classical surface, this guy has the same matter entropy as this guy. So these two are the same. And as a result, we would have that the von Neumann entropy using this formula for QL union QR is equal to S, the same thing, of QL bar union QR bar. Okay, the identification, the way it goes is that the disconnected surface in the entropy of quote unquote the wormhole is equal to the entropy, the entropy of the disconnected contribution for the entropy of the wormhole is equivalent to the island contribution of the entropy of the radiation. That's this statement here. Okay. Similarly, the trivial surface contribution to the entropy of the wormhole is equivalent to the semi-classical entropy of the entropy of the radiation. Okay, and thus we get page curves for everyone. if you look at, if we imagine we're evolving from this slice here t equals 0 to some later slice here, or rather, okay, let me go. This is the last. Well, I have 2 other slides, but let me discuss this slide slowly. So here, this rising piece, the green curve was the trivial surface for the computing the entropy of the wormhole, while the red line is the semi-classical entropy for computing the entropy of the radiation, and they are equal because they are complements. Similarly, if you look at the disconnected contribution here, it's going to be equal to the island contribution for the radiation. And that's going to be constant for all time using all these CFT tricks, or the trick about factorization. And so we see that both systems have a phase transition at the page time, which is what we needed. And the final thing I wanted to emphasize on this slide is that the funny thing is that we didn't have to change anything about the quantum state, right? We only changed the formula. In particular, the state of the rate of the interior of the black hole or the wormhole is actually extremely mixed. You have all these quanta here, which are entangled with the quanta in the bath. So let me highlight that, emphasize it. But it does not contribute to the entropy or to the entanglement between them. At least if you look at the disconnected surface. Any questions about the last 3 slides, including this one? I did have 2 more things to say before ending.
Are you assuming here factorization of the Hilbert space, and can those corrections give you any problem?
Good. I am not assuming the factorization of the Hilbert space. In fact, this is in the next slide. I will argue that this is evidence that the Hilbert space does not factorize spatially. So I'll get to that in a second. But any questions about the identification of this calculation with the previous one? Maybe I should go here. Or was that point clear? Okay, so let me say the last few things I wanted to say, and then I'll open it up for questions. Okay, the point, let's see, where is this? Yeah, this point here about even though the interior of the wormhole has a lot of mixed radiation, but nevertheless, it does not contribute to the entropy of the wormhole, it should be understood within the context of entanglement wedge reconstruction. In particular, what's happening is that the ADS bulk is being shared by the different parts of the bath. Okay? For example, before the page time, you should think of the interior as being part of the boundary, or part of what I called Q, which you should think of as the wormhole as seen from the outside. The entanglement wedge of this region is the domain of dependence of the homology region of that sigma, which is given by this entire region. This is the entanglement wedge of the wormhole at t equals 0. The entanglement wedge of the bath at t equals 0 is just these 2 red shaded regions. But if you look at times after the page time, the tables have turned. The interior now is inside the entanglement wedge of the radiation. Radiation, which is what I call Q bar. So it's not part of the wormhole as seen from the outside. Okay? The entanglement wedge of the wormhole is just this tiny region here, union this tiny region here. the inside is part of the entanglement wedge of the outside. The final comment I wanted to say was the implication for firewalls and for information transfer. For firewalls, I will just take 10 seconds and I can say more if people have questions. Basically, the idea is that you don't have the firewall argument, so it's a non-paradox. It requires factorization of the Hilbert space, but from entanglement wedge reconstruction, we have that HA is actually part of H. It's a subsystem, not element, it's a subsystem of HR. So even though B is entangled with A, but A is part of R. Okay, so that's how you avoid the firewall paradox. And finally, a comment about information retrieval. When I discussed this last time, I forgot to mention that this question about when do you get information outside of a black hole, when does it escape, is called the hidden Preschool experiment. And this entanglement wedge reconstruction story, it gives a realization of this. In particular, if you throw in a message at some time, the message escapes the entanglement wedge of the wormhole after a scrambling time, exactly what you'd expect from these quantum circuits considerations, and it becomes part of the radiation entanglement wedge, right? It falls in, and now it's part of the radiation entanglement wedge, so it's now secretly part of the radiation. So this gives an amazing picture that the mechanism for things to escape the black hole is for them to just fall in deeper. So maybe I should stop at that cryptic comment and take questions. Thank you.
Great ending. All right, questions for Ahmed.
I might have a question. So it's about the semi-classical approximation that you're making. So I was wondering, because we're saying that on the right-hand side of the quantum extremal surface formula, we're taking the Hawking radiation to be semi-classical. I mean, to just be the semi-classical part of it. Whereas on the right-hand side part, it would be like the whole description of the Hawking radiation. And so I understand that, but from a physical perspective, how would you separate the two? Like, I don't know, maybe it's a blurry question, but.
No, it's not. This question was the main topic of many conferences and discussions and so on. Like, it's why am I, like, I'm saying that this is crazy, right? I'm saying that the entropy of this thing is actually small, but clearly in the semi-classical answer, in the semi-classical calculation, that entropy is large. And then I'm saying that the way you fix this is not by changing the state, but rather by changing the formula that computes the entropy. Some people have described this as an accounting trick. When you're trying to evade taxes and so on, which you shouldn't do. Anyways, so the point is that we don't understand why gravity is giving us this. I will derive this next time. The point is that I'm not putting in this. I'm not putting this in by hand just to get the right answer. But it turns out that it's actually it's secretly a deep thing about gravity, that it's a deep thing about like we already saw an example of this where gravity gave us, quote unquote, the right answer without telling us how to actually go about it. For example, in the Gibbons-Hawking entropy calculation, it just said, just compute the action on this semi-classical geometry. Here we want to know what the we want to know what the entropy is of the radiation. What it could have given us it could have given us the exact quantum state of the radiation, and then we should just compute trace rho log rho to compute the entropy. But it's not giving us that. It's telling us, never mind what the actual state is, let me give you a quick and dirty way of computing the entropy. Just assume that it's semi-classical and apply this modified formula. In the very beginning of my lectures, I call the information paradox not a paradox, but a problem, because we understand how to compute the entropy, and we know, quote unquote, Hawking's mistake in computing the entropy, but we have no idea of how to compute the matrix elements of the density matrix. Like, gravity tells us what trace rho log rho is, but it doesn't tell us what the matrix elements of rho are. It's kind of analogous to what you guys heard from Phil and Steven Schenker. They can compute this spectral form factor as a function of time. Gravity can give you the smoothed out version, but it can't give you the wiggles. And I think it's the same thing here. I hope I've addressed your question. If not, please ask again.
Yeah, I think it helps more or less. I guess my question was, so what you're saying is that there's the radiation coming out, and it seems semi-classical, right? Because the Hawking's calculation is semi-classical. But you're saying that in fact, secretly, there's some like quantum gravitational degrees of freedom that also come out somehow, and we don't really know how. And that's why we're allowed to equate the semi-classical bit to actually something bigger. I mean, not equate, but consider it part of something bigger, or?
Kind of, like in the sense, well, I wouldn't, so I would, so you said some quantum gravity thing is coming out. I would say that if you're doing experiments with the radiation, if you're asking very simple questions, like correlation functions of simple field of just a small number of local operators, let's say, then the answer that you get is consistent with a semi-classical answer. But if you try to if you're trying to measure something extremely complicated that measures the detailed correlations between the Hawking quanta, that's like, as you described, the quantum gravitational thing coming out. I guess I would just call it like the imprint of quantum gravity on the radiation. Then you would need something more. I have the semi-classical description of the radiation is not a good description. Does that help?
Yeah, I think that helps. Thanks.
Mm-hmm.
I have a question.
Yes, please.
So, I mean, in the originals, all the original setups of ADS-CFT, you never had a bath. And now all of a sudden you include this bath. And you specifically said it's supposed to be non-gravitational. And then you're collecting radiation in it. What if it was, what if the bath was, what if you didn't like enforce that it was non-gravitational? I mean, what if you just collected radiation somewhere at like the boundary without the bath?
Mm-hmm.
What would happen then?
Yeah, in principle, everything should also go through. So let me draw a picture for you. So let's suppose, oh, sorry, this doesn't stay. I'm drawing a time slice of ADS, okay? So suppose you have a black hole here that's radiating. And let's imagine that you collect all of the Hawking radiation and you put it somewhere here, like in some collection here. Like you have, let's say you had a big Dyson sphere and you're collecting the radiation, and then you transport it to some spaceship here, okay? Then imagine computing using the regular holographic description for entanglement entropy. You're computing the entropy of a region like this, okay? In the standard way, you would say that there's an RT surface that does something like this. or a quantum extremal surface that does, yeah, a quantum extremal surface that does something like this. But it would also, well, this is one possible one possible RT surface. But you can also have, this RT surface can also have an islet. You can get something disconnected. So just applying the regular rules for computing holographic entropy in ADS-CFT in this contrived setup, you should expect that you'd get something similar to what we had here, where you, in this computation, you also have an island, which is the inside of this red region, which captures all the modes that are entangled with the modes here. Hope that answers your question. By the way, this was analyzed by Busso, and I have I forget who, Maria, I think. So first name Maria, forget her last name.
Okay. Thank you.
Yeah, I also don't. I'm also not sure of the order of these two letters, if it's OU or UO.
OU.
OU, okay. There you go. Any other questions? I went fast on the last few slides. I can explain things again. People want.
That's going to be my question. If you could take a bit more time on the last few slides.
Okay, which one? Were you okay with the page curves for everyone?
Sure. Yeah. I think it was the last two. I think that were the fastest. The
okay.
Firewall non-paradox, maybe.
Okay. Okay. Good. So in the firewall paradox, we had these two postulates where to have vacuum at the horizon, A had to be entangled with B, but in order to have unitarity, the combination of B union R had to have less entropy, less than or equal to the entropy of R, of the union of R and B has to be less than or equal to the entropy of R. Basically because by unitarity, the black hole entropy cannot, it's maxed out. It can't become larger than the thermal entropy. And then we discussed last time that these two conditions violate strong subadditivity. So the quantum state of this quantum state that's required to satisfy postulate 1 and postulate 2 is not a consistent quantum state. And so we said that it's a paradox, so you have to break one of them, and then we broke this one. That's what we discussed last time. But an assumption of this no-go theorem is that the Hilbert space of A, B, and R factorizes. That these are three distinct quantum systems. However, we learn from entanglement wedge reconstruction over here, entanglement wedge reconstruction at times after the page time, the inside of the black hole is part of the radiation. It's part of the entanglement wedge of the radiation. This means that for any operator here, well, any suitable simple operator here, you can find an operator which acts in this region, which has the same effect as the operator inside. Okay, like literally, like if I'm literally inside the black hole, and you do something here, you can send signals to me. Not only that, but you can also read what I'm doing. So entanglement wedge reconstruction in this context implies non-locality. And so HA is a part of HR. So this assumption is broken. And so we were not justified in using the strong subadditivity formula. And so it's not a paradox. So we don't have the paradox. In the evaporating context, even though I didn't discuss this last time, in the evaporating context, one says that the weird quantum state is that B has to be entangled with A and it has to be entangled with R. So that's impossible. You can't have a entanglement is monogamous. B can't be maximally entangled with two systems. But if A is part of R, then you're not entangled with two different systems. They're the same system. So that was the firewall paradox. And did you also want me to explain this, or was it clear?
There's time, but we could do it after. People might have other questions.
Okay.
I guess
Yeah.
I had a quick question.
Yes.
Sorry, I don't want to interrupt. Sorry, Professor.
Go ahead. Go ahead.
Okay. I was just wondering, I think earlier, like maybe the first lecture, you mentioned that there was an analogy to like Reiner-Nordstrom black holes, and you maybe like drew up a replica picture. And I was just wondering if in higher dimension, if this would just extend straight through and you just find one copy of JT, or if there's a replica trip to isolate like these other factors. Yeah, I just wondered if how higher dimensional black holes work. Sorry.
Yeah, good question. In higher dimensions, this thing was analyzed only for special cases where because there's an issue that we don't know how to compute matter entropy in higher dimensions, except for very special situations. And these formulas that I'm talking about, it involves extremizing area plus matter entropy. We need to know the matter entropy precisely in order to find the quantum extremal surface precisely. So we don't know how to do that, but there are general arguments that say that that predict the existence of quantum extremal surfaces, even in higher dimensions, but they're not as precise as what you can do in 1+1 dimensions. That's all I can say.
Thank you. Thank you.
Mm-hmm.
Any other questions?
Maybe since we're still recording, maybe I should try to explain this thing a bit more.
Mm-hmm. Go ahead.
Yeah. Okay, this was quick. So I was saying that let's imagine that we're after the page time, where say at this time here, the wormhole has the following entanglement wedge, but the bath, well, not but, and the bath has this entanglement wedge. So clearly, if anything is in this part of the space-time, it's now part of the radiation. Now, the thing that I was imagining the following thought experiment. It's suppose at this time here, one throws in a particle. At around these times, the entanglement wedge of the wormhole will look like something like this. Too much. This would be the entanglement wedge of the wormhole at this time here. So it clearly contains the message which you throw in. At least, as by the wormhole here, I mean the wormhole as seen from the outside. The quantum system here that is dual to this part of the space-time knows about the message. But then as you evolve this thing to the future, and more to the future, and more to the future, you lose access to the message. So here now I'm just comparing the initial time and the final time. The message is no longer inside the entanglement wedge of the wormhole. And it has entered the entanglement wedge of the bath. So, and the amazing thing is that the time it takes for the wormhole to forget about the message is precisely the scrambling time. And there's an odd fact here that the scrambling time is not log of the entropy, but rather the entropy, the Bekenstein-Hawking entropy minus S naught. Just sort of showing that the degrees of freedom responsible for the zero temperature entropy is not involved in the dynamics somehow. That's just a side comment. Anyways, so this is an interesting mechanism for how information, quote unquote, escapes the black hole. What this says, ultimately, my final comment, is that there's an experiment you can do here, which is able to detect this message. And that's all I had to say.
Actually, one more thing that would bear clarifying probably is that given all this, why is it compatible with using the assumption that the entropy of a region is the same as entropy of its complement? In other words, you don't have this spatial factorization that would have underlined that statement. So why is it still consistent?
Good. There are two things. There is there was the entropy, well, in the when discussing the semi-classical entropy, which appeared, we had area or 4G Newton plus semi-classical entropy. When making statements about the state that makes an appearance here, you're assuming the semi-classical picture, and so you say that the entire state, that the matter state everywhere is pure, like it's pure on the entire slice, and you do actually have tensor factorization in space. That the entropy of the blue region is equal to the entropy of the red region in the semi-classical state. Okay, so that's one comment. The other comment is that so this was the quote unquote semi-classical description. In the exact description, I'm using black because it's serious, the total state is what I drew, is the sort of the quote unquote complete system. Or maybe said differently, this formula that we've been discussing tells you that the state of the black of this region here is actually pure. So this means that the entropy of this region is equal to the exact entropy of this region. Okay, so these are two different things.
Great.
Excuse me, a very quick question, follow up on what you said on this last slide. You said that there is this violation of locality in this late time, but and so you can basically perform an experiment in the path and retrieve information that is behind the horizon. So, but to actually probe that non-locality, do you have to make a very, very complex operation or not? And
yes,
also, like, not only behind the horizon, but also in the region of the entanglement wedge, which is on the left, but outside the horizon, yeah, that region, is it still, that's probably still a violation of locality, and is that also very, very complex operation to probe something in that region?
Let me see. In general, yes, you need to do a very complicated operation here that can change anything there. But there is actually a trick. I can give you guys the reference there is a trick. Let me see. Well, first, yeah. So in general, yes, but there is a trick that you can do using quantum teleportation, like the Gauss-Jeffress wall kind of thing, where you can extract information in a relatively simple way. But that's a special thing about the very special setup. But you're right that in general, you need to do something extremely complicated here to affect things here. And the complicated thing you need to do here, the operator itself needs to depend on the gravity path integral. And the gravity path integral of your operator connects to the physical space-time through a wormhole, and it affects things in the entanglement wedge. but you'll see more of this tomorrow.
Great, excellent. I think we should, in the interest of time, stop the recording.